see.
Okie doke. Okay, folks, here we are. It is the physics video lecture, Physics 105B video lecture 5. I'm going to start with some announcements, namely about our email, homework, and lecture notes. So every Friday, no later than 6 p.m., we want to have 2 emails. So we'll just separate out the notes and the homework. So first one, here, let's write Friday 6 p.m. Email. First one, your name, Physics 105B. Notes. And then the second one is your name, Physics 105B, homework. So the notes are always the notes Monday, Wednesday, Friday of that week, or whatever lectures happen that week. You know, if we have Labor Day, then we'll have a day off. But yeah, the notes are just that Monday, Wednesday, Friday, and they're due, since it's a morning lecture, they're due at the end of the day. The homework, whatever you have by then, we'll start getting a little more dialed in as to what is due when. You certainly don't have to turn anything in that was assigned on like today's lecture, but the stuff that came before, that was assigned before that, you want to try to get in by Friday 6 p.m. So that should make things work pretty smoothly. Okay, I'm going to have a lot of emails to field, but if I always see your name, the class, and either notes or homework, that should work out pretty well. Oh, also, especially for this class, make sure you use a good PDF converter or something so that I can actually print things out, so I can make a clean printout of everything. So PDF files, because generally I can read pictures well enough, but I can't print them out. So PDF files so that they can be printed out well. You can figure out how that works. Other than that, we're just going to keep moving on. And because of the circumstances that we're under here, the notes really take on a greater importance, because really you learn over time that the production of a good set of notes is just a major thing. If you were to decide you wanted to teach a class, you'd produce these great set of notes, and it would take you all manner of time, and it'd be a huge learning experience. So the notes are just full of stuff that if you just see it once, you don't really know it. But if you practice it, you can practice anything in the notes, and it's going to build you up. Good. So let's get started. We're doing Lagrangian mechanics now, and we made it to an important point with that kinetic energy expression. So let's just review a little bit and then get back to that kinetic energy. So Lagrangian mechanics can be based on a variational principle. That comes in handy later on. So, and the shorthand for a variational principle is that this thing holds true here. L is kinetic minus potential energy. It's very significant because you have a scalar here. Okay, when systems get complicated, figuring out what Newton's laws are can be very difficult. But if you can simply obtain the kinetic and the potential energies, and you do it right, then what follows is just automatically correct. So you get a correct set of equations of motion out of it. And the equations of motion, regardless of what coordinate system you use, see, the minimum principle doesn't care what coordinate system you used, right? It's just we have a minimum principle. So whatever coordinates you used, you have, oh, I should even write, at this point, L is equal to L of Q1 to Qn. So you've now used generalized coordinates, Q1 dot to Qn dot and T. That's the general form of the Lagrangian if you convert it the way we've been doing with what we ended up with last time. So yeah, you've got this, and then your Euler-Lagrange equations, dl dq I dot minus partial L partial Q sub I equals 0. Doesn't matter what the coordinate, Cartesian, spherical, polar, you're just following this rule, and that gives you your equations of motion, however many degrees of freedom you have. Remember, they have to be independent, very important. And we also have a principle that the sum of partial L partial Q I dot times Q I dot minus L itself, L is outside of the summation, minus L is equal to a constant. Conserved quantity, as it were. Now, these formulas are the translation directly into Lagrangian mechanics of what we had in the variational calculus. So definitely look back at your formulas for the variational principles and make sure you see how these are the direct translations of, because we proved those things rigorously, as it were. And now we're just translating by plugging in these different symbols. Okay, we had y's and x's, and now we have, and then we had positions and times, and now we have generalized coordinates and times. Okay, direct translation. So now what we have to do is remind ourselves how you actually construct the Lagrangian. And we already got started on that, so constructing the Lagrangian. And the first example was with Cartesian coordinates. So L is equal to 1/2 m x dot squared, y dot squared, z dot squared, minus u of x, y, and z. What would this be? This would be a single particle in a potential of all three variables. Okay. My next example, how about free fall? Free fall and projectile motion. So if you have free fall, we'll choose the z-axis to be vertical, and we'll just say u is equal to mgz, right? That's the simple potential energy for being in a vertical axis, z. You know, you could have x, y, and z like that. And then we do this, but we just have u of z and not u of x, y. So the free fall Lagrangian, if we're still living in 3 dimensions, x dot squared plus y dot squared, there's a plus sign, plus z dot squared minus mgz. So they're a free fall. Yeah, so Cartesian coordinates, no problem. Let's keep going. Yeah, we'll go right under these here. So how about a third example? What about the harmonic oscillator? Then we have L equals, since it's T minus U, it's 1/2 mx dot squared minus, we could say 1/2 kx squared. Simple harmonic oscillator. Okay. Am I numbering things? Yeah. How about example 4? Now example 4 was when we did last time, a particle in plane polar coordinates. Yes. Plane polar coordinates. And we had L is equal to 1/2 m r dot squared r squared phi dot squared minus u of r and phi. That would be just the general expression for Lagrangian and plane polar coordinates. And here we saw we had some generalization, because this is where we were getting into generalized coordinates. So what we're going to do now is repeat this major expression I had derived, and then we'll keep going with that. So we had, well, put that underneath here. Yeah, I can actually put that underneath here. And then I'll save that board for, so example 5. This is what we ended with last time. L is equal to 1/2 double sum ij, a sub ij of the coordinates, which I'll just write as a vector for all of them, all n of them, qi dot qj dot minus u of q1 to qn. I'll write them out individually. Okay. So this is a very general Lagrangian of the type in which energy is conserved, which we don't know yet, but which I'm just telling you. Well, actually, we kind of know it. You have a potential energy like that. Energy is probably conserved. So this is what we had arrived at last time. I want to say a little bit more about this a sub aij, because this is a very general form now. So what we have here, aij of q, you can think of it as a matrix if you want. It's, n times n entries. They're functions of the coordinates, and what we can require is that aij equal abi of q. So when you're constructing a Lagrangian, it isn't always symmetric. And here I'm claiming that it's always symmetric. When you construct it, if it's not symmetric, you make it symmetric, okay? If it's not symmetric, you just add these off-diagonal elements together and divide by 2 and give 1/2 to one side and 1/2 to the other. Symmetric, so I'll just write or make it symmetric. So that's one property we have of this. And the entire kinetic energy term is a quadratic form. Because it came out of a sum of squares, it's what we call a positive definite quadratic form. Something that we run into a lot in mathematics and in physics. So positive definite quadratic form. So this t equals 1/2 double sum aij qi dot qj dot is a positive definite technical thing you can look up. Positive definite means it's always positive. Okay. Quadratic form. Quadratic form. And in your notes you have the construction of this, and this aij is pretty frightening thing in general, but in special cases, any specific case, you just construct it systematically, and it is whatever it turns out to be there. Example number, where we 4, Aij, what did we say that was? It was M0, 0, mr squared. So make sure you understand that. You've got this expression, you've got this expression, and you have this one right here. Make sure you put that together and see what it means. Okay. And of course it's symmetric, right? And it's very common that they only have the diagonal elements. Okay, so that makes things simple. But there will be problems, especially when we're doing oscillations, small oscillations, where the off diagonals play a big role as well. Okay, so we'll get both kinds. Good, so we had those. I should start formulating some homework problems. Yeah, here's a good one, just to get in the groove here. Let's start by writing out the Euler-Lagrange equations for all of these examples, 1 through 1, 2, 3, 4. So examples 1 through 4. So homework. Write out the Euler-Lagrange, that's what I always call it, is EL equations for these examples. 1, 2, 3, and 4. Really, it only gets interesting at the plane polar, but in all of these, you'll see you're just writing out Newton's law. Okay. In the plane polar, you know, we didn't so much use the equations of motion when we did the central force problem last semester, because we went straight to the energy, right, when we actually integrated it. But yeah, if you had U of R and not phi, this would also be the central force Lagrangian. Okay, good place to revisit it. So yeah, you'll be writing out the equations of motion, the Euler-Lagrange equations. These are all kind of trivial. Example 4 is interesting because of it being the central force problem. Central force problem when there's no phi dependence. Okay, good. Let me check the time on this operation here. Very good. Okay, so with this, we have some basic formalism. Now I'm going to do a couple of more concrete systems. What we do is, what we do is set them up, and we'll end up working with them for a while. So the next system I want to, next, some mechanical systems that we'll be analyzing. And first I'll just, so that it's written down here, note example 4, wasn't that one, example 4 with U equals U of R is the central force Lagrangian. Okay, we're gonna come back to that. One plays a big role, of course. Central force Lagrangian. Good, so here's an interesting example. I think I had shown that the other day. So we have a frictionless track, there's an x-axis, here's our mass M, and to this mass M we've attached a simple pendulum with a massless rod M and L, and we need the Lagrangian for this system. You can kind of imagine what it does. If it were at rest and you had the pendulum going, then the large mass would be going back and forth as well, okay? And the whole thing could glide along and do something similar. Okay. That would be for small oscillations. Now, so if we want to get the Lagrangian, we have to start constructing the kinetic energy is a half m v sub m squared, capital M, plus a half lowercase m v sub m squared. Okay. And the potential energy is equal to mgy if I have a vertical y-axis, okay? So I have a vertical y-axis. But I can't just write this down in that form and call it the Lagrangian yet. I have to start with this and then construct the correct form for both of these. And this one as well. So next thing we have to do is next independent coordinates. So what we have to do first in the Lagrangian method is find those generalized coordinates. And we will do that. We'll find the generalized coordinates up there. I should have written something in, but I should get a stick where I could put this thing in, and it gives me an idea and fill in, but I'll go back up to my picture here. So that I don't have to keep drawing. So here's the thing. We're going to just take some point on this mass, could be the front edge, it doesn't matter, and give it the label capital X. I'll use an uppercase X here. And then we have lowercase x and y for the small mass. Okay. But these coordinates x and y are not independent of each other, because this thing can of course only swing through an arc. So they're not independent, and that's why we're required to go to this angle here, and then we'll have this coordinate capital X right there. Okay, so that's the argument. Now let's go ahead and do it. And that will be as follows. So we will have T kinetic energy is 1/2 capital M capital X dot squared plus 1/2 lowercase m lowercase x dot squared plus lowercase y dot squared. U is equal to mgy. Still not a Lagrangian, okay? Here we have x equals capital X plus L sine of phi. Okay, this is where it gets interesting. Okay, forget that dot right there. We're just taking the capital X to be right where this thing's attached. Okay, because at this point we had to make the decision. Okay, so lowercase x is uppercase X, which is just that position there, not this one, plus L sine phi, and then y is equal to minus L cos phi, and now we have to take dot and squared. So x dot squared is equal to capital X dot squared. Oh, can't square it either. There are some steps here. X dot is equal to capital X dot plus L cos phi dot. y dot is equal to minus L sine phi dot. Right, we've done this kind of thing before, so we're just putting it all together. Now we're going to do x dot squared plus y dot squared equals capital X dot squared plus 2L cos phi x dot phi dot plus L squared cosine squared phi dot squared, and we're going to add the y dot squared, which is this L squared sine squared phi dot squared. So here we get something nice. Cosine squared and sine squared add up. We just have L squared phi dot squared. This is a cross term that we cannot argue away. We have this thing here. So now we're ready to write down the entire Lagrangian, and that is 1/2 capital M capital X dot squared plus what I have here, 1/2 lowercase m capital X dot squared plus 2L cos phi X dot phi dot plus L squared phi dot squared. Good, fit that in there, minus mgy. And y was negative L cos phi, so it's minus mg. And I like to keep this, the minus signs kind of burgeon in Lagrangian mechanics, so I'll put it here, minus mg/L cos phi. So there's the Lagrangian. It's not yet in the form we wanted it in the standard form. So we will do that by noting that we have capital X dot here and here. So finally, I'm going to write L equals 1/2 m plus m x dot squared. Okay, that takes care of that. Then I have plus 1/2 lowercase m, and I'm going to take this 2L cos phi x dot phi dot, and since I have two of them, I'm going to write it twice, 1/2 m L cos phi x dot phi dot. Time to erase right here. Plus 1/2 m L cos phi dot x dot plus 1/2 m L squared phi dot squared minus negative mg/L cos phi. What a mess. So here I did two things. This was that symmetrization that I was talking about before, right? These two really only appeared here as 2L with the 2 times L x dot phi dot in the original Lagrangian. I broke them up into these two. It makes no difference for the equations of motion, but for that matrix, it does make a difference. So should I add this to the homework? Yeah, I'll add it to the homework. But I'll just point out what you have to do, but you guys can then do it. Homework for this Lagrangian Aij of x and phi equals, if you're looking for a 2 by 2 matrix, And so I've set it up so that we can put it in standard form. And you can see what you're going to have. That's why I wrote it this way. In fact, I'm giving you the answer completely here. With some parentheses. Oops. Back answer, there we go. Okay, so this standard form involves factoring out the 1/2. Then you have everything function of the coordinates in the matrix, and then you have the generalized velocities, okay? So yeah, this is this t equals 1/2 double sum aij of q qi dot qj dot. This is what it is. And you can see we have the xx, the x phi, the phi x, the phi terms. Now, these two actually are functions of the coordinates, right? These two are functions of the coordinates. The other ones are formally functions of the coordinates. They're just constants, but they can be functions of the coordinates. So this is a really important example because it had the full matrix with the off-diagonal elements. They've been symmetrized. And I could ask you to write out the equation of motion, but I won't. This is already, and this is not a really complicated system. This thing already has some pretty involved equations of motion, but you might think about what the equations of motion are. I want you to write out the whole thing. When we do the theory of small oscillations, we'll choose phi to be small. Cosine phi will be 1, and things will simplify quite a bit. And then this matrix will be a very important object in the theory of small oscillations. So yeah, this is a good formal way to get these Lagrangians written down, get that matrix form of those coefficients. You see they're functions of the coordinates, and you got the cross terms. Solving this equation would be very, very difficult analytically. I mean, analytically, forget it. It's too highly nonlinear and coupled nonlinear equations. For people doing technology work or in mechanical engineering, this is actually what they do. They set up Lagrangians, because that way, you know, they're doing numerical work, they can get the correct equations of motion. Really the only way to get the correct equations of motion. And you see, this system's pretty simple. If you're talking about a motorcycle or something, it'd be a whole other ball of wax. Okay, that's a great example. This one you really want to study and understand what we've done so far. Let's see what else. So yeah, make sure you've got this, because we'll be referring to this when we do small oscillations. Yeah, I could set up an even worse small oscillation one. You know, I have a great idea. Since I've already done this one for you, let's do a related one for homework, okay? The related one for homework is so basic, but why not? Yeah, I will start anew. So we had this, and here's another good problem. What we'll do for the related problem is add a spring to this thing, and you'll largely just be copying it down, but it'll be good exercise for you. So homework, construct L for this system here. Frictionless, of course. There's X. So we've got a spring here. The mass. P. You know, it's the same coordinates, but there is another potential energy term here, okay? Other potential energy term. And there's a real, there's a nice one we could do too, and we'd be done with these. This is a good example. Yeah. L4. Now this is a related system, and that is we have a frictionless track, y equals f of x, with a local minimum, and we'll again call this M. Well, we'll rename things a bit this time. We'll call this M1. It's the same old pendulum system, no friction, length L, angle phi. But now y is equal to f of x. Okay, this one gets interesting. Maybe we'll put it on the next homework. I think I want to start talking about this one with you. So this will give us a good collection of stuff to work on. So yeah, this one now, we have a problem here. They're both moving in two space, but because this one's on a track, it really only has 1 degree of freedom. And this one being connected with a rigid rod also has 1 degree of freedom. So we're only going to have 2 degrees of freedom. And this is our x-axis as well. So we're really doing something similar. We have t equals 1/2 m1 x dot squared plus 1/2 m2 here, I'll call them x1 and x2 for the moment. Okay. x2, y2, x1, y1. Okay. x1 dot squared plus y1 dot squared. And then x2 dot squared plus y2 dot squared. Okay. But as we said before, this is not independent, nor are these independent. So you can't just use this in the Lagrangian. We do have to go down to 2 degrees of freedom and not 4 degrees of freedom. So constructing the Lagrangian for this thing is kind of interesting. What we do is we have y sub 1 is equal to f of x sub 1. Okay, so now y sub 1 dot is equal to f prime of x sub 1 dot by the chain rule. Okay, so that's the key here. And then you go through the same process I did before, then it's actually very similar. Okay, so f prime of x1 dot. And so now we've reduced x dot squared plus y1 dot squared into something that reduces, so I'll even write this down. So 1/2 m1 x1 dot squared plus y1 dot squared equals, and I can get rid of this here, equals 1/2 m1. Now we have x1 dot squared 1 plus f prime of x squared x1 dot squared. See how that happened? Common factor squared this right here. Okay. Everything else works out about the same. And yeah, I'm going to just say a couple more general things and then leave it right here. So that's a fair amount to work on, and this one problem, we're doing a few variations of it, is very instructive, okay? We can actually, when we get to small oscillation, we pull these things out and keep analyzing them. One thing you'll notice, once you get these Lagrangians written out, you don't even want to write out the equation of motion. You can, but it's just very long and tedious. But you want to be confident that you can write them out, because it's just elementary calculus, right? Chain rules and careful derivatives. And what you'll notice is that these systems are already very, very complicated. This is the simplest way to treat them too, okay? So you can realize we're looking for simplifications. As physicists, the real complications we would leave to the engineers. We want to, get overarching viewpoints that allow us to deal with these things. And the one that we have so far is that, just to reiterate, complicated system, if we can just write down its Lagrangian, we can be confident that we'll get the correct equations of motion out for it. And these complicated Lagrangians, when we, narrow them down to say the small oscillations problematic, then again, they simplify beautifully and we'll have a really nice theory. So don't think that we're getting in really deep and wild and woolly stuff. This is all gonna have a pleasant conclusion. But I think this is enough for now. You've definitely got a lot to work on. So you make sure you understand these notes and then do these constructions, and that'll be good. So what are we going to do after this? We'll work our way into conservation laws. And conservation laws in the Lagrangian formalism are very beautiful. Okay, so we've got some good stuff coming up. Okay, see you guys later.